All right, we're moving on to section 2.5, where we will be evaluating limits algebraically. In this section, there's a couple things that are going to seem a little bit more formulaic, a little bit more algorithmic. This video, this first introduction in 2.5, is really to justify why this algorithm that seems almost like a recipe, why it works. Okay, I'd never like to teach a method without explaining or showing why this works. In math, you should never be blindly doing something. You should always be asking, why does this work? Why am I able to do this? So, why are we able to do this procedure? Well, first, let's go ahead and take a look at the procedure here. So, if you are ever presented with a limit, so for instance, if you are tasked with evaluating, what's the limit as x goes to 3 of x squared minus 9 over x minus 3. All right, how are we going to do this limit? We're not going to use numerics. We're not going to use a graph. We are just going to do this algebraically. Well, let's follow this procedure. So step 1 here says, actually, right before this, you will begin by attempting a direct substitution and check to see what you get. And then these are the 3 possibilities of what we could get. So we want to plug in our value 3. So if we just plug in our value 3, what are we going to get? Let's do this off to the side. We're going to get 9 minus 9 over 3 minus 3, which goes to something that looks like this. 0 over 0. This puts us in category number 2, which is we get something that is 0 over 0, infinity over infinity, 0 times infinity, infinity minus infinity, and there's even other different indeterminate forms we could get, like 1 to the infinity or something like that. In this case, those are a little bit more exotic, but for right now, we're going to see things like 0 over 0. That's pretty much what we're going to see right now. So this is indeterminate. It means you cannot, based on this result alone, you are unable to determine what the correct answer is to this limit. Some people may try naively to say that, oh, well, 0 over 0, isn't that just equal to 0? That's not true. You can't do, first of all, we can't divide by 0. Anytime we divide by 0, there's some nonsense going on. But in particular here, we're not just dividing by 0. Because if we found ourselves, let's say 3 divided by 0, this is not indeterminate form. This is just undefined. Undefined and indeterminate are different. So if we get something like a non-zero number in the numerator and 0 in the denominator, we find ourselves in case 3, which we'll talk about. Essentially, this means there is a vertical asymptote, and that we know that the graph at that location does something like this, or possibly they both go up, or maybe they both go down on the asymptote. But regardless of what the left and right hand limits are, we know that there's a vertical asymptote at that location, which automatically tells us that the limit does not exist. Now, if the left and right hand limits both go up, we could say equals infinity. If the left and right hand limits are both going down to negative infinity, we can say the limit equals negative infinity. But in either case, D and E. Here, 0 over 0 is not actually a vertical asymptote. This means there's something funky going on, and we just have to figure out what it is. So, this sort of scenario puts us into case 2, which means that we will have to rewrite and attempt to evaluate the limit. So there's some sort of algebraic manipulations that we can do, and we'll learn what sorts of manipulations work for what your expression looks like. Depending on what this expression is, certain algebraic techniques are better than others. So sort of like a classification. I always think of limits as first plug in to see what you get, because sometimes you do luck out. Sometimes with a limit, like for instance, if I just made this, if I just made this plus and plus, then this whole thing would turn into 9 plus 9 and 3 plus 3, which does not go to 0 over 0. It goes to 18 over 6, which is 3. And since this is a real number, that puts us in the category 1, and that means we're done. That's the answer to the limit. So really, your first step is to just plug in and see what you get, because that's going to put us into one of these 3 categories, and then we have a next step to take if we land in categories 2 or 3. If we land in category 1, we're just done. Okay? So this algorithm, this recipe that I'm describing here, this works for a certain set or classes of functions. It doesn't work across the board, okay? So what's really important here is that we are assuming here that the function we're taking the limit of, so whatever goes right here in this box, whatever expression we're taking the limit of, that expression is not piecewise defined, so it's not a piecewise function, and that the only functions contained in the expression are the familiar functions, elementary functions. So things like polynomials, or maybe trig functions, sine, cosine, tangent, or the other ones, cotangent, cosecant, secant, things like that. Exponentials like e to the x, or maybe even like 5 to the x, exponential functions. Logarithms, so ln x. In this class, we won't work a ton with like log base 3 of x, for instance. We usually just work with ln, natural log, but logarithms. And root functions, so things like the cube root of x. And rational expressions, which really just means we have a polynomial divided by another polynomial, much like the case that we had with x squared minus 9 over x minus 3. That's a rational expression. If we have things like that, so pretty much every function you've ever seen, more or less, basically all the functions that your calculator has a button for on the front, those are your elementary functions. Things that are non-elementary, I give an example down here of something called the floor function. The floor function, we're only going to talk about the floor function for positive x values, or sorry, at least non-negative x values, just because we'll keep it simple. But the graph of the floor function is right here. Sometimes we call it like a step function here. What it does is it returns, it basically is the round down function. It gives you a whole number. So if I plug in, what's the floor of 2.3? Well, that's just 2. What's the floor of 4.9? Well, that's just 4. Okay, it just gives you the greatest whole number contained in that number. Okay, so for instance, this breaks our algorithm up here. And this is because the floor function is not an elementary function. It's actually a piecewise defined function. And you can see from the graph of the floor function, this thing's got discontinuities everywhere. So, if we were naively to use our above algorithm for the floor function, so for instance, this is a bad example. This is not supposed to work, and it won't work. If we go ahead and task ourselves with evaluating the limit as x goes to 2 of the floor function of x, well, our first step in our algorithm is to just plug in. So if we just plug this in, we get the floor of 2, which is 2. 2 is the largest whole number contained within 2. So we get the floor of 2 is 2. And then if we follow our algorithm, we would find ourselves landing in case number 1 because we got a real number as our answer. We didn't get something like division by 0 or an indeterminate form, such as 0 over 0. So this would be the answer to the limit. So based on our algorithm, this would say the limit is equal to 2. But clearly that's not true. Look at the graph here. The left-hand limit is 1. The right-hand limit is 2. The left and the right-hand limits do not, they do not agree because there is a jump discontinuity here. So the limit actually of the floor function as x approaches 2 does not exist. Really, when I say a function that's non-elementary, it usually means there's a lot more information contained in this expression than what meets the eye, and it's those finer details of the function's non-elementary definition that could cause our algorithm to break. But there are nice ways to handle limits of piecewise functions. We'll get more practice with that, but for right now, this algorithm only works for non-elementary, it only works for elementary functions and things that aren't piecewise defined. If they're non-elementary functions or they are piecewise defined, you have to take a closer look at things. You may still be able to apply this algorithm in certain areas of the function's definition, but not globally.